Hello and welcome to my channel. My name is Asif Maroof and this is Infoverse Tech channel on YouTube. I try to bring new technologies and concepts to my subscribers. So today we're going to look at Kafka for event-driven data pipelines, and Kafka is the K in SMAC stack. So we will look at some key concepts and architecture of Kafka, and will help decide if Kafka is a good choice for your organization. So let's get started. So as I mentioned, Kafka is the K in SMAC stack, and the other components are Spark, which is a fast general engine for large-scale data processing. Mesos, now known as D21Q, is a cluster resource management system. Akka is a toolkit for building applications on JVM. Cassandra is a highly distributed database, and Kafka is the K in SMAC stack, which is a high throughput, low latency messaging system. And today our talk and presentation will be on Kafka. So a quick introduction. Kafka was originally developed at LinkedIn in 2010, and it was then open sourced to the Apache Foundation, and it is currently deployed at 100,000 plus organizations globally, and this is a testament to popularity of Kafka. Commercial support is provided by Confluent, and the founders of Confluent are the ones who actually wrote the code originally while working at LinkedIn. Competitors include RabbitMQ, ActiveMQ, IBMMQ, and similar. One of the key features is Kafka allows decoupling of producer and consumer. It's scalable to billions and billions of messages per day. As an example, Netflix uses Kafka to process hundreds of billions of messages on a daily basis. It has fast throughput, very low latency, fault tolerant and highly available, and can also guarantee and provide durability, zero data loss, and it has what is called an immutable log. So this is an interesting slide, Kafka powered. So who is using Kafka today? As we can see, it's used across many different industries. You can see you have travel sites, you have payment systems, we see databases, banks, financial institutions, automotive, and so on. And I believe everyone on the hearing this presentation can read these and recognize most of these very popular brand names. We have Adidas, Twitter, Square, Trivago, Datadog, Shopify. So all of these organizations are or have deployed Kafka in their organization and enterprises, and using it to create event-driven data pipelines. So this is a slide where I call organizations today before Kafka. So as we can see, any typical organization will have multiple databases, multiple applications, and all talking to each other. And over time, it becomes a highly connected system. It becomes difficult to scale and very difficult to troubleshoot in the event of a failure. And the time after Kafka, where we can really simplify things. So as you can see on the left-hand picture, you have producers on the top, consumers consuming that data, and in between is Kafka Cluster, which is tying them all together like glue. And producers and consumers we will go in detail, but for now, producers can be any entity that is generating data. It could be an IoT system, it could be a database, it could be an application. And consumers could be other systems, other IoT systems, other applications, other databases which are consuming that data. It could be a dashboard for monitoring. The possibilities are endless. The right hand picture shows the same concept: producers, consumers, and you can see that applications, databases, all of them are communicating to each other, and they're unifying entity in between as a Kafka cluster. So the way I structured this presentation is to start with a high level picture and then drill down into the details. So the way to read this is from left to right. We have producers producing data. It's coming in and it's pushed into the Kafka cluster. And on the right hand side we have consumers who are pulling that data and consuming it. Some of them might be processing it, changing the data. Some of them might be adding to it. Some of them might be just picking up the data and passing it on to a backend database or a visual dashboard or something similar. And in between we have Kafka cluster with brokers, which is another name for nodes, and we have another system called Zookeeper, and the function of a Zookeeper is to maintain the cluster and manage it. And we'll see we have a separate slide to talk more in detail about the Zookeeper. Another view of how Kafka can tie in all these disparate systems. So we have at the lower part of the picture, we have these producers, could be metrics, logs, transaction data, IoT data. They're feeding into a Kafka cluster, and consumers, you have an online application or stream processing, or even offline batch processing by Hadoop. So this is another way or use case where Kafka can be very useful to implement. So quick definition of a streaming platform, which allows publishing and subscribing to streams of records. It can store streams of records in a fault-tolerant, durable way, and can process streams of records as they occur. And Kafka is generally used for two broad classes: building real-time streaming data pipelines, building real-time streaming applications that can transform or change that stream of data in real time. And Kafka is really a combination of a message queue and a publish subscribe system. So let's talk a little more about Kafka producer. So producers can or do create messages, and they write to a topic. Topic is similar to a location where data is being written, let's say maybe a file or a database record. And producers may or also called publisher or writers on some other systems. If a topic has multiple partitions, which means that it's writing to different areas in order to improve scalability and durability, as we'll see in a later slide, the producer will try and load balance between all partitions. So as the producer is writing data, it will try to load balance among all the partitions of that particular topic. And the producer can be configured to write to a specific partition using a key, and this ensures the writes go to the same partition instead of being like written round robin manner. And a use case could be that we are, as an example, we are tracking a customer as he goes through an e-commerce shopping platform, and we are tracking his movements. So it makes sense to make sure that that particular customer is always the events that that customer is generating are coming and being recorded on the same partition. So a little more detail about the producer and broker topic relationship. So we can see here that on the left hand side picture we have three brokers or three nodes. The producer is writing data, and each topic X has three partitions. and partitions are just other areas for writing data, and this will help increase the scalability of handling all those messages, especially if the producer is producing a large number of messages. The rate of production is very high. The picture on the right just provides more detail on how a topic with two partitions, how it is writing. As the producer writes, the offset, which are the numbers or the areas where the data is being written, they move from left to right. So the partition 0, the one on the top, is currently producer is writing to offset 12, and on the lower partition 1, it's currently writing to offset 9, and you also have a consumer that's reading from offset 9 and offset 7. Now a very key concept here is that the log or the data that's being written is immutable. So once it's written in, let's say, offset 4 of partition 0, it cannot be changed. I can read it multiple times from a consumer, but the data remains unchanged. This is a really important property of Kafka topics. So a topic is, as you mentioned, like a log to which records are written, and it can have multiple partitions for redundancy and scalability. And topics in Kafka can have single or multiple consumers that subscribe to the data that's being written. So in the left hand side picture, we see as we move from 0, which is the first offset, which is the beginning of our writing, to this topic partition, and we move to the right. As time increases, the writes are being written and the offsets keep increasing in a linear fashion. The right hand side picture shows a similar depiction of a topic with 4 partitions, and you have messages coming. So the first partition is currently being written in offset 13, of partition 1 and offset 9, partition 2 and offset 11, and so on. And it's okay to have different offsets while it's being writing, because data being written and data being consumed could have different rates, and that's a very normal use case. This slide shows a relationship between topic, partition, and replicas. So we have data coming in being written to a topic. In this picture we have 3 partitions, which by the way is also the default for topics. So each topic, if we don't make any changes, will have 3 partitions, and partitions will have 3 replicas, which is the default. So by default, if we don't make any changes, any partition will have 3 replicas. So here, for simplicity and clarity, I'm just showing partition 0 with 3 replicas, and let's see how they are residing on these brokers. So we have 3 brokers, and you can see in broker 1 it's partition 0 replica 1, on broker 2 partition 0 replica 2, and so on. And similarly, partition 1 will have 3 replicas, partition 2 will have another set of 3 replicas distributed uniformly across the number of brokers. In this case, they are matching. There are 3 brokers and there are 3 replicas. So replicas help with durability. So in the event one of the brokers goes down, or even 2 go down, we still have the capability to recover messages. We talked about the partition, and partition is really a component of a topic, and is distributed over servers in the Kafka cluster, and each server is able to handle data and requests for a share of the partitions. Each partition is replicated across a configurable number of servers for fault tolerance, and this is called the replication factor. And as mentioned earlier, this is 3, which is the default. Now each partition has a server which can act, or which acts as the leader, and it can have 0 or more followers. And shown in the picture in the lower part of the screen, you have partitions which are leaders shown in red, and you have the corresponding followers shown in blue. So the way to read this is, for broker 1, partition 0 is the leader, and then in broker 2 we have partition 0, the second copy, and on broker 3 we have partition 0, third copy. So all the writes are coming into the leader, while the followers, they ensure that they are in sync with the leader. So at any given time, the followers or replicas are always in sync with the partition leader, and that's another important concept here. So when we talk about replicas, Kafka has a default replication factor of 3, meaning there are 3 copies of each partition on different brokers. It's obvious that a higher replication factor will provide higher availability, but it comes at a cost. A replication factor of n will allow a cluster to lose n-1 brokers while still able to read and write data to the topic reliably. Kafka ensures each replica for a partition is on a separate broker. This may impact availability if all the replicas for a partition are on brokers on the same rack. So in order to mitigate this, Kafka uses broker.rack configuration parameter, which can configure the rack name for each broker, and then replicas for a partition are spread across multiple racks, and this guarantees higher availability. So very highly configurable options that Kafka comes with. A Kafka consumer can read messages from a topic partition. They're also called subscriber or reader on other systems. Consumers can keep track of offset. Offset is the location where the message is stored, and read from that location. If we add additional consumers, they can handle a higher rate of incoming data. So as shown in the picture, you have a producer that's writing to offset 12 at this moment in time, and you have 2 consumers who are consuming that data. Consumer A is consuming from offset 9, while consumer B is consuming from offset 11. And as mentioned earlier, consuming data does not change in any way the data that's residing in those offsets. The data is immutable. So there's another concept of consumer group, and it helps if the consumers are from the same application and they're consuming that data. So put them in a consumer group. As shown in the picture here, you have a consumer group with 3 consumers, and they're consuming data from 4 partitions. So consumer 0 is consuming from partition 0, currently at offset 6. Consumer 1 is actually consuming from 2 partitions, partition 1 and partition 2, and consumer 2 is consuming from partition 3. The thing to note here is that the same 2 consumers of the same consumer group cannot consume from the same partition. This is by design to make sure that there is no data corruption. Now let's move on and look at some additional use cases of consumers. So figure 1 shows a topic with 4 partitions and a consumer group with 1 consumer, and as we can see that consumer is consuming from 4 partitions at the same time. It does show that maybe 1 consumer is not enough, so we add a second consumer to the group, and now that's evenly distributed. So partition 0 and partition 2 are being consumed by consumer 1, while partition 1 and partition 3 are being consumed by consumer 2. So this is a slightly more scalable way of looking, as 2 consumers are consuming that data. In the third picture on the right, we see 4 partitions, and we have 5 consumers, and there's a 1-to-1 mapping. However, consumer 5 is idle because it cannot, since it's in the same consumer group as the other 4, it cannot consume from the one of the partitions, because they're already being consumed by the other consumers. Having an idle consumer is not that bad, although there is a slight cost of overhead. But in the event that one of the consumers dies, this can quickly take its place without any loss of data. So it's not a bad idea to have a spare consumer running, even though currently, as shown here, it's running idle. Another concept here is that we've introduced a second consumer group with two consumers, and as we can see, for consumer group 1 there's a one-to-one mapping, and as we add consumer group 2, we are now load balancing between the two consumers in consumer group 2. So this is all of these that we've shown here are very, very valid configurations for consumer groups. We've spoken about the Kafka cluster. So Kafka cluster is run on these nodes or brokers, and these can be common off-the-shelf components. It stores streams of records in categories called topics, and each record can consist of a key, a value, and a timestamp. The picture below shows a 3-server broker cluster or 3-node cluster with 2 partitions for topic A and 1 partition for topic B, and we have a producer sending to these topics, and we have consumers that are consuming that data. Zookeeper is an application that manages and maintains the Kafka cluster. It is also including management of the topic metadata and ensures that the consumer offset is also managed. Zookeeper tasks include coordinating brokers, cluster topology, and maintaining a consistent file system. It also is responsible for managing the leadership election if one of the brokers goes down, and also handles the topic leader, partition leaders, and their followers. So as we are building this, the concepts up here, it's very clear that Kafka, as it sits in the middle, it can handle different kinds of producers producing different types of data, different formats, and we on the other side we have consumers who are consuming that data, and data can be coming in at different speeds, in real time, in batch, in bursts, and it can have different sizes, different file formats, and we have consumers on the right hand side which are consuming that data. So they introduced the concept of connectors, and connectors allow different types of systems to talk to each other. So as an example, we have a JDBC, a MongoDB, and a MySQL source or producer that's producing that data. So we will use the connectors that understand how to talk to JDBC, understand how to talk to MongoDB, understand how to talk to MySQL. And on the consumer sides, or the sinks, as they're pulling in that data, we have an Elastic, we have a Cassandra, and we have HDFS connectors. So all of these connectors understand how to talk, which formats, which file formats to understand. So having a connector in between allows that communication to flow very seamlessly. Some of the connectors available on the Confluent platform include most of the popular ones. So as shown here, you have Amazon S3, Confluent Replicator, Elasticsearch, Sync Connector. You have an IBM MQ, JDBC, JMS. Let's take a look at some additional ones that are available on the Confluent website, and I'll just read out the very popular ones. So we see in Amazon Kinesis, we have an AWS CloudWatch, Azure Data Lake, Azure Event Hubs, HTTP Sync Connector, InfluxDB, Google Cloud Data Pros, Google BigQuery. We see a Redis sync connector, a Salesforce connector, ServiceNow, Splunk, MQTT, MongoDB, Microsoft SQL, Postgres. So there are hundreds of connectors, and as you're building up your applications, you will be sure to find a connector that will work for you. So as we mentioned, a Kafka Broker is like a node, and it receives messages from a producer, assigns it an offset number, and processes that data to disk, so it's not lost. It can also communicate with the consumer, providing the messages that are written to disk. A single broker can scale to handle millions of messages per second. As part of a cluster, the broker will function as controller and is responsible for assigning partitions and monitoring for failures. Each partition is owned by a broker, which is also called the leader of the partition. When we talk about order and availability, you are guaranteeing that the messages sent by a producer are appended in the order they are sent. And as we saw in the previous slide, that this is an immutable log, and the offset number moves linearly. So if a record M1 is sent by the same producer as a record M2, and M1 is sent first, then M1 will have a lower offset than M2 and appear earlier in the log. And the M1 or M2 can be read multiple times by multiple different consumers without changing the data in any way. And a consumer instance will see records in the order that they are stored in the log. So these are very important concepts from a Kafka perspective, and understanding how the data moves and how data is handled. Availability for a topic with replication factor n, the cluster will tolerate up to n-1 failures, server failures, without losing any records committed to that log. Kafka is able to process real-time streams of events from input topics, do some additional processing on the data, and produce a continual stream of data to output systems. It is also like a storage system, because incoming messages are persisted to disk. The retention period is a highly configurable parameter. It's either time-based or size, which means that it can default to 1 week of persistence or 1 GB, whichever is reached earlier. It allows producers and consumers at different speeds to communicate without loss of data. So this is a really important concept, and we touched briefly in the opening part of the presentation to say the decoupling of producer and consumer. So a producer could be producing messages as millions of messages per second, and if we have not scaled our consumer to keep up with that pace, the incoming messages are not lost. They are stored inside Kafka, and the consumer can either scale up, we can add more consumers in that consumer group to try and match what the producer is sending. Even if the consumer falls behind, as the producer slows down, the consumer can pick up those messages without any loss. In fact, some organizations store terabytes of data in Kafka queues. So there are typically 4 core APIs, which are the producer, consumer, streams API, and connector API, and they allow various interactions to happen and can be used by scripts from the console to run Kafka commands. And as the name suggests, they are either producing data, consuming, streaming the data, or allowing connectors between 2 disparate systems. Some Kafka defaults, size of message sent is 1 megabyte. Size of message that can be consumed is up to 10 megabytes. Number of partitions per broker, a thumb rule calculation is 100 by B, 100 into B into R, where B is broker and R is replication factor. Number of partitions per topic, that's 1. Kafka data file size is 1 GB. Replication factor is 3. And retention is 1 week of data or 1 gigabyte, whichever is smaller or whichever is reached first. So Kafka is highly configurable, and you can see if you just look at producer and consumer, there are so many configuration changes, tuning that we can do, and it can help to improve your Kafka deployment. So some of the interesting ones are like acknowledgements. So if we set the acknowledgements to 0, which means that the producer keeps on sending without waiting for an acknowledgement, that's the fastest. We can also set it to 1, which means that it'll wait for acknowledgement for at least one of the partitions. And I can also set it to all, which means that is the slowest, but also the safest and most durable, because the producer will wait for all the acknowledgements to come in from all the nodes before moving on. Compression type can be Google Snappy, gzip, or LZ4. Batch size, linger, ms, all of these are very configurable and provides you a way to fine-tune your system. The maximum request size is 1 megabyte, and the receive and send buffers are set to -1, so that it defaults to the OS, using its default settings. On the consumer side, you have the minimum bytes to receive, the maximum partition fetch bytes, auto.offset.reset. This is interesting because if in the event that a consumer goes down and when it rejoins and starts reading, it can either go to the beginning of the offset, start from 0, or it can start from the latest, the last one that it was reading before it went down. And in addition to being configurable, this is also application dependent. So the application might require you to flush everything and then start a fresh set of data, or the default is fine, which means, okay, I was reading from offset 6 when I went down. When I come back, I restart reading from the last one that would be in the next in line, which might be offset 7. Partition assignment strategy. Default is range, although by experience it results in an unequal number of partitions per broker, but the round robin works better in assigning those partitions. However, that's the default, and again, these are all configurable. In terms of security, we can encrypt data between producers and consumers. We can authenticate using SSL and SASL. We can authorize the clients with ACLs to determine whether or not a particular client will have access to some topic. So very granular, and we can have an audit log to track access, both authorized and unauthorized. In terms of software, the current version is 2.4. You can run it on Windows, Mac OS, Linux. It requires Java version 8 or higher. Requires Zookeeper, Broker, and Kafka APIs. In the cloud, you have AWS MSK, Azure Event Hubs, and Confluent Cloud on Google that can provide you the similar capability. Some quick review of Kafka command tools. So to start a Kafka Broker, once it's installed in your user local, you run the kafka-server-start.sh script. The second example is creating a topic name test with a single partition and only one replica. So you're running it from bin kafka-topics.sh create. Go to use the local 9092 port. Replication factor is 1. You're overriding the default of 3. One partition, and the name of the topic is test. You can then run a describe topic, which will display what you just created. So once we run that command, it shows that we have a partition count 1, replication factor 1, topic is test, 0 partition, 0 leader, 0 replicas. You can write to that topic. So user local Kafka bin Kafka console producer. You write to the topic test. You write test message 1, test message 2, and then I can use the consume API to read that from that topic, and the configuration I say is from beginning, so from offset 0, so it reads test message 1, test message 2, and also reports that I've consumed 2 messages. So some of the key takeaways: Kafka is a modern distributed system running as a cluster and able to handle terabytes of incoming data. It allows that decoupling or matching of producer and consumers. So producers could be producing at a different rate, consumers could be consuming at a different rate, but the Kafka architecture ensures that no message is lost. It's high durability. It's a very powerful messaging application. Multiple consumers can access the same data without any performance loss or data loss. It supports queuing and publish subscribe concepts, provide replication, thereby increasing resilience to failures. Kafka can provide storage of data from bytes to terabytes, and it can handle real-time processing of events. Use cases include messaging, log aggregation, monitoring, and stream processing. And connectors for hundreds of source and sync systems are made available by the Apache Foundation and Confluent. So thank you very much for watching. I look forward to your comments, and hopefully we'll work to bring you new technologies. Thank you for watching.